Ready to start? This is the last talk of the Analysis and Math Physics seminar for 2025, and Ben is going to lecture on estimates for Ricci Solitons in dimension 4. Please.
Thank you. I'd like to thank Milo Brenna and Milo Delos for the kind invitation to speak at this seminar. Today I'll be talking about estimates for self-similar solutions of Ricci flow, especially in dimension 4, and they're called Ricci Solitons. And so the first thing I want to do is motivate the Ricci flow as a heat equation for metrics. And so we start with infinitesimal notion of distance and angle, and that's the Riemannian metric. It's a symmetric two-tensor, and from that we have this notion of parallel transport, the Levi-Civita connection. So that allows us to differentiate vector fields. And when you're computing in Ricci flow, it's often convenient to use local coordinates, xi. And here we have writing the Levi-Civita connection in terms of its components using the coordinate system. And then we get the Christoffel symbols, which have 3 indices. And then we have the standard formula, which exhibits it as one derivative of the metric. And then from any connection, we can get curvature. So in this case, we get the Riemann curvature tensor, and tracing that, we get the Ricci tensor. So I've only shown the formula and local coordinates for the Ricci tensor in terms of Christoffel symbols. So they're quadratic, the last 2 terms. And then the first 2 terms are one derivative of the Christoffel symbols. And so that's 2 derivatives of the metric. And so it's very much related to basically the idea of taking the Laplacian of the metric. And so formally, the Laplacian is you take 2 covariant derivatives. Whoops, we'll get it right. You take 2 covariant derivatives of a function on our manifold, and then we trace, and in local coordinates is given by this expression. And in particular, we can look at various coordinate systems. And one type is called harmonic coordinates, where the Laplacian of the component functions are all 0. And then that's the same thing as this trace of the Christoffel symbols being 0. And there's another variant of it. In any case, if you choose such harmonic coordinates, then we can express the right-hand side of the Ricci flow, which is minus twice the Ricci tensor, as the Laplacian of the metric component. So just invariantly, if we took the Laplacian of the tensor, we get 0 because covariant differentiation of the metric is 0. But if we just take the components of the metric and take the Laplacian of those functions and express this in harmonic coordinates, then we really see kind of the Laplace operator there up to lower order terms.
What are the stalls?
So those would be just various contractions. So that would be like a G upper ij would be a G inverse, and then maybe a G upper j KL as another G inverse, and then there'd be like partial I, G, J, K, but all different indices and just written out that way. And then repeated indices would be summed until you do it in a way so that you get a 2 tensor. So in that case, we have 10 components. So that means 8 of them would be contracted. So some of these would be, these will use some of the contractions, some of these together would be contracted like that. So it's just saying that the exact form is not important in the sense that this is lower order in the metric G. Okay, and so since it's a heat equation, there's short time existence and uniqueness. So we can start on a closed manifold. That means a manifold, a compact manifold without boundary. And then it doesn't matter what initial smooth metric we choose, you can run the Ricci flow for a little time. how long depends on the geometry of the initial metric. And this solution is unique. And then the flow breaks down exactly when the curvature goes to infinity. Okay, so that means if the curvature stays bounded from time 0 to capital T, then you would be able to extend it past time capital T. So if T is the maximal time, provided T is less than infinity, then the sup of the curvature over space and time must be equal to infinity. Okay, so those are just the very basic results about Ricci flow in general. And so we said that it's a heat equation, but we had to use harmonic coordinates. But now we can compute evolutions of various geometric quantities. And of course, that can be done invariantly. Here I've expressed it in local coordinates. And so we'll next look at the scalar curvature, which is the trace of the Ricci tensor. And then what we see is something that really looks like a heat equation, except we have a nonlinear term. It almost looks semi-linear, but the Laplacian depends also on the metric. And so what you can see is that extra term here is non-negative. In fact, there's an algebraic inequality just for like matrices. You can think of this as just choosing components Dij equals delta ij, the Kronecker delta function. And you have a simple inequality like this. And so plugging that into the equation for the scalar curvature, you have a heat type inequality like that. So what it shows is that the curvature wants to move upward, at least the scalar curvature. And the scalar curvature is just one type of curvature. But if we apply the weak maximum principle, namely we apply the first and second derivative tests from multivariable calculus, we see at a minimum, the Laplacian is not negative, and so one actually shows that basically the scalar curvature wants to increase. And what you can do is, if we want to say what the parabolic maximum principle says, is we simply just drop this Laplacian, turn that inequality equality, consider that ODE. So maybe give it a different variable like ds dt equals 2 over n s squared. And if you want to look at the worst possible case, take s at time 0 to be minus infinity, and you have this solution on the right-hand side. And then the solution to the heat equation is at least that solution to that ODE. And of course, if you knew you had, well, the initial metric is smooth, so you can get a better bound than this. But this is true independent of the initial condition. Okay, so the scalar curvature wants to rise and all that. And now the next thing I want to discuss is the topic of today's talk, which is self-similar solutions of Ricci flow, also called Ricci Solitons. And here, the structure is the following. So we think about a Riemannian metric. So we have a manifold, a Riemannian metric, and a function, a scalar function on the manifold. And then a real number, and usually the real number will be normalized to be +1, 0, -1. Only the sign of lambda will matter. And you you just impose this equation here. And so basically we have 3 instances of the same equation depending on the sign of lambda. And the names are, when lambda is positive, that's a shrinking soliton. So the idea is that if you have such a structure, there's a lemma that says that you could actually turn G into as the initial condition for a Ricci flow. And that, so what that means is that if we take the negative of this equation, at least the negative Ricci would be like the time derivative of the metric. And this will be a diffeomorphism term. This is actually the same as the Lie derivative with respect to the gradient of f of the metric. So it's you can think of it as an infinitesimal isometry. And what that means is that if you think of this not as a static structure, the way it's written, but as a Ricci flow, then the time to the metric would be basically negative lambda times the metric. So if lambda is positive, that means it will be shrinking. Lambda 0, it's basically static in some sense, up to diffeomorphisms. And then if lambda is negative, it's expanding. So the idea is if you want a singularity to form in finite time, it should be shrinking, right? Because if you just take a sphere and you shrink it, the curvature goes to infinity. If you expand it, it goes to 0, and there's no singularity. So that's why the first two instances are relevant to singularity formation in Ricci flow, shrinking solitons and steady solitons. And when the potential function is trivial, namely a constant, then we get this Einstein metric. So it's really self-similar without having to invoke the action of the diffeomorphism group. Okay, so it turned out to be important to couple the Ricci flow. Sorry, that's wrong. That should be with the conjugate heat equation. And that's first observed by Perlman. And so there's certainly fundamental work of his on this, which I'll describe in a moment. And then later work of Bamler in this direction. Okay, so the idea is we want to think of on the space-time, we have, the volume element at time t, dt, and we can think about what's the adjoint of the heat operator. And so the idea is the scalar curvature represents, under Ricci flow, how the volume form evolves. There's actually a minus sign. But in any case, when you do the calculation, if you take the heat operator, this, ddt minus Laplacian, and you compute its adjoint, then you get this extra term due to the fact that the family of metrics is not static and evolving by Ricci flow. Okay, so what one can do is one can look at the Ricci flow, the first equation, and then basically the second equation is the conjugate heat equation. And then the third equation is just introducing a positive number depending on t, which has a scale. And the derivative of the scale is equal to -1. Okay, so these equations were introduced by Perlman. And then it's useful to think about basically the potential F defined this way. So if U is the solution to the conjugate heat equation, then F we'll call the potential. Okay, so maybe we can think of U as being a conjugate heat kernel, so starting as a delta function. And then if you think of the Gaussian, then the function should be like distance squared over 4t, right? So what that means is you have the option of looking at the solution to the conjugate heat equation, or what's basically equivalent, the potential function F defined this way. But then we can think of F as a proxy or a substitute for the distance function, or distance squared. So this would be a more natural way than just looking at the Riemannian distance between 2 points, because that would be like a fixed time slice, right? It'd be better to have a space-time distance. And so there are other notions of space-time distance, like Perlman's reduced distance, which is very fundamental, which I will not.
Excuse me, so that U that you have at the bottom of your slide, that doesn't necessarily solve the other equation.
Yes, we'll assume that this satisfies this equation.
So it does?
Yes, okay. And then we'll consider, then F will satisfy
the other. Then you gotta find F that way?
Yeah, so F will satisfy another equation. Okay. Yeah. And then that's the way Perlman originally.
On us, yeah.
Yes, yeah, exactly. So Perlman originally wrote it for the equation for F, and then later he talked about U.
Okay.
Yeah, but it's all bullet. Okay, and what's really an amazing formula is Perlman's entropy formula. So it looks very maybe strange at the beginning, but the idea is you really, if you think about, he first defined the energy where he only had the R plus grad f squared and then the e to the minus f dv. And that action, I guess, appeared in string theory. And you can kind of think of it as a variant of the total scalar curvature or Einstein-Hilbert action, because you could just take f to be constant, right? I mean, just to think about what that would give you, and that would be the integral of R dv. Okay, so if we really didn't have f, then that's what it'd be. And now it's written a way, or is defined in a way that is actually related to the fundamental solution to the heat equation on Euclidean space. Okay, so what you find out is that if you take basically f to be distance squared divided by 4 tau, then what you're going to get is that this entropy will be 0. So you think about this entropy kind of being extreme. In a certain sense, it will be extremized on Euclidean space. Okay, but what's actually very interesting is that this is, we can think of this as a Lyapunov functional for the Ricci flow. Okay, so the idea is that we're going to have a Ricci flow, but we're going to couple it to the conjugate heat equation, and we're going to have a scale that's kind of decreasing in time at a steady speed of rate of -1. And then what we find out is under those equations that had been down earlier, Perlman, then he proved that the evolution of entropy is monotone.
Isn't it kind of difficult to solve the conjugate heat equation? I mean,
okay. So what you do is you run a Ricci flow. Once you have the Ricci flow, you have your space-time, then you solve it backwards. So you never solve it forward.
well, of course not.
Yeah.
That's,
And so then there's no difficulty because it's basically just like a heat equation with a potential and a varying metric, but that's fine. It's like you're given your family of metrics first, and then you solve that. And then it becomes very useful. Okay, so what you see is actually, the shrinking Soliton equation in the sense that if this norm was 0, that would be a shrinking soliton. So this is in singularity formation that will kind of predict that, or in some instances actually show some singularity model must be a self-similar solution. So it's very important for this entropy to the evolution. I mean, the fact that if you set this left-hand side to be 0, then that means that the solution is a shrinking soliton itself. Okay, and so in 2D, what happens if you're on a smooth manifold, then you get convergence to constant curvature, and that's what Hamilton proved almost all the cases. And I did one small case at the end. And then one can generalize this to isolated orbifolds with isolated singularities. So we want to think of a space not just modeled on R2, but R2 mod ZP, where the ZP action is generated by a rotation of R2 by angle 2 pi over P. And so you kind of see things that look like cones, but we don't want to think of those cones as being singular. So that means if we have a structure on this orbifold with a cone point, and we want to say, is this function smooth or not? We take a local lift. So locally, we can lift to a p-fold cover, and we're on R2, and then we talk about the smoothness of the lift of the function or of the metric even. Okay, so what that means is when we discuss orbifolds with isolated singularities, so they're modeled on R2 mod ZP, then we can talk about smoothness of the metric, smoothness of all these structures, etc. And what happens is that not all orbifolds with isolated singularities have, finite covers. Closed ones have finite covers that are smooth surfaces. And the exceptions are what Thurston called teardrop, which has one cone point, an S2 with one cone point, or an S2 with two cone points, which we call a football. And those orbifolds don't have constant curvature metrics. The football doesn't if the orders of the two cone points are not equal. But what the Ricci flow does is it converges to a shrinking Ricci Soliton metric here. Okay, so this kind of, when you go to this category, you see the necessity of looking at Ricci Solitons. So Hamilton's philosophy was kind of like, why did this influence his proof in dimension 2 in the case of smooth manifolds is because when you do analysis, you can't tell a difference between whether you're on a smooth surface or on a smooth two-dimensional orbifold with isolated singularities. I mean, any technique that works on smooth surfaces works also on orbifolds. And the fact that those bad orbifolds don't have constant curvature metrics affects analysis. So what he actually proved is he proved conversions to a shrinking soliton, and then he proved the shrinking soliton on S2 must have constant curvature. Okay, so there are a few examples which I will only just mention the most basic examples and not really get into these more advanced Kähler examples. Okay, so it would be interesting to first look at shrinking solitons, and then the interesting thing that Perlman observed actually is somewhat fundamental, even though it's a simple observation, but it affects kind of the philosophy of looking at Ricci flow, is that we can think of static Rn as a shrinking soliton. So the idea is that it's not moving, so how could it be shrinking? But the idea is we can multiply the metric by 2, and that's isometric to itself. So comparing to the double, it looks like it's shrunk, right? So the idea is that we kind of just imagine with static Rn under Ricci flow, it's not moving, and then we identify one point with another point. This world line would be just going straight up like that. But it's really, you should think of the diffeomorphism invariance of Ricci flow. And perhaps there's no reason to really identify, I mean, well, most of the time, the same point in space at two different times. And then we have cylinders, which are just spheres across Euclidean space. Einstein metrics are basically the simplest examples of solitons. And then there are a few Kähler examples. The first one is called the FIK. You can think of it as like as C2 with one point blown up. So it's like connected some with CP2 bar. It's a holomorphic line bundle over CP1 with first Chern class -1. But the main thing is that it's asymptotically conical. And so that's very interesting. So in dimension 3, and it works in real dimensions 4, even real dimensions 4 and above. And in dimension 4, real dimension 4, there's a unique shrinker with this property that's U2 invariant and all that. And it's asymptotically conical, and that cannot happen in dimension 3. And this other so-called BCCD, the names are Bamler, Cifarelli, Conlon, Durrell. And that you can think of as CP1 cross C blown up at one point, or in other words, S2 cross R2, but connects some with CP2 bar, like that. So one is asymptotically conical, the other one is asymptotically, in some sense, like S2 cross R2. Okay, so next thing, after seeing a few examples, or at least referencing them, is to look at the basic equation. So the idea is one of the first things you can do with this two tensor equation that we have for a shrinking soliton. Here I normalized lambda to be 1 in this case. So this will be our equation for the metric G and the function F right here. And then you can just take the divergence of this two tensor. We get a one form or one tensor, covariant one tensor. And there's a second contracted second Bianchi identity, which says that divergence of the Ricci tensor is 1/2 the derivative of the scalar curvature. And if you plug this in and let's see, so yes, so you have to commute covariant derivatives, and there's a Ricci identity floating in there. And then you use the, I think use the Solitine equation there. You finally end up with this equation, which says that the derivative of the scalar curvature is twice the Ricci tensor applied to the derivative of the potential function F. And it turns out that you could just substitute this Ricci, replace it by the Hessian and the metric, and then rewrite it so that the derivative of this whole thing is 0. So by adding a suitable constant to F, we can get this equation. So this is another fundamental equation here. So, so what we know is that we have a shrinking soliton, the scalar curvature plus the gradient of F squared equals F. Okay, so you could take Euclidean case with where scalar curvature would be 0 and F would be, you know, like norm x squared divided by 4, and that you'd see that equality. And then what you can do is instead you could take another divergence here, and you basically get the Laplacian of metric. There's some other terms here that combine, so you actually get something like this. You get this elliptic operator. I guess it's called the drift Laplacian, and it's also referred to as the F Laplacian in Ricci flow. And so this elliptic operator on R satisfies this equation like that. And kind of somewhat similar to the parabolic heat equation satisfied by scalar curvature. And that makes sense is because the diffeomorphism change is from here, is drift. Okay, so that means we should think of the scalar curvature as satisfying a nice elliptic equation. And one of the question is what is true? So we'll call the shrinking Ricci solitons for short Ricci shrinkers or even just shrinkers. What is known about them? Well, we saw that the Gaussian shrinking soliton had a very nice potential function. And it turns out remarkably that all shrinking solitons have a very similar potential function in the following sense. So first of all, the first result is that if you're not on Euclidean, this is due to Bing-Long Chen, and if you're not on Euclidean space, then the scalar curvature must be strictly positive. So this is basically just a maximum principle. Well, it's rather weak conditions. We don't assume that the curvature of the solid, it's most interesting when the soliton is not compact. We don't assume the curvature is bounded. We only assume completeness of the metric. So this has to be localized. But with Perlman's like changing distance formulas and all that allowed, after his works, allowed localization to work much more effectively. So this was proved later. Okay, so what one can see is once you have R positive, then you get this elementary consequence. And then what that says, if we fix a point, then we see, we fix a point, so just think of this as a number here, and then we see basically a quarter distance squared as the upper bound. Okay, so that means there's a very trivial, nice upper bound simply because the scalar curvature is positive and from this equation here. What's also remarkable is there's a qualitatively basically the same lower bound. So it's also, it's a lower bound, but it's a quarter, and this will be the positive part of what's inside here. So it's really distance squared here and a different numbers here, but it's basically 1/4 distance squared again. So it's very well constrained, kind of very similar to the Gaussian potential function. And so that would make you think that maybe the shrinkers are very rigid and all that, but it's still not known except in dimension 3. Okay, so we're interested in these shrinking self-similar solutions, and they would satisfy some elliptic equation. What can we say about the geometry? Well, we know that we're not on the Gaussian, then this curvature must be positive. But it can decay very quickly, and the answer is no, it has a quadratic lower bound. Okay, so this was proved a while back with Bo Yang and Peng Liu.
So are these all for 4 dimensions, or are these general dimensions?
This one is in general, yes. Okay, so yeah, and the idea is, so n will be a dimension, the idea is simply a maximum principle. So once you have the very nice control of the potential function, you can use this quantity. So the key is to find the right quantity, and this works very well right here. And actually, by just applying the maximum principle, this pops out, turns out, which is a bit remarkable that the structure is like that, because usually, like a global maximum principle, to get an estimate that is like that is pretty rare. Okay, and this is sharp because this is exactly the rate of decay of the asymptotically conical shrinker that has that quadratic decay, including this so-called FIK, Kähler Ricci Soliton. And then if we have a steady Ricci Soliton, then we have this equation, r plus gradient f squared equals 1. One can show that. So one thing that's interesting about that, immediately this tells us the scalar curvature is uniformly bounded on a steady soliton. So what we have before for the shrinking soliton is that the scalar curvature a priori has a very weak upper bound, because if you look right here and you see that the scalar curvature is bounded above by the potential could grow quadratically. And remarkably, it might be true that this is the best possible upper bound for the scalar curvature. And then, so we have the following result of Munteanu, Sung, and Wang. So that for a non-Ricci flat steady Ricci Soliton, just assuming that the potential function is non-positive. So the idea is, for a lot of examples, it will be, let's say, positive Ricci curvature. It'll be concave, and that will actually limit to minus infinity at infinity. Then you get this exponential lower bound for the scalar curve. So it's a much weaker bound. And there's a reason for that. And so with Bo Yang and Peng Liu, we actually prove this assuming first that f must go to infinity, to minus infinity as the point goes off to infinity. But they improved our assumption to something much weaker, that you only have to assume that f is not positive. And then they're both sharp because in the second case, there's a so-called Hamilton's cigar soliton. In physics, it's called Witten's black hole. And that has exactly this decay of the scalar curvature. But famously, Perlman proved what Hamilton had conjectured, that the cigar soliton cannot be a singularity model. So if you assume you have a singularity model, you could hope for something better than exponential decay. Okay, so, and then it turns out with Bandler's techniques, with Pak-Young Chan, Zulu Mao, and Yunjia Zhang, we showed that if we also assume we're in dimension 4, and we have a steady Ricci soliton. So the previous results, we did not assume any dimension restriction, but now we also have to assume that's a singularity model. Then you can improve the scalar curvature lower bound to quadratic. Okay, so that would be asymptotically conical, and that would make sense for the shrinking case. But in the steady case, one of the prime examples is Bryant's soliton. It has positive curvature. It looks like a paraboloid, and the curvature decays only inverse linearly. So that's true for all the other examples too, as far as we know. So one can ask, this is just kind of an artifact of the proof that you can only do this. Maybe the question is, can you improve it to inverse linear decay for steady solitons, more in line with the known examples? Okay, so those are some of the scalar curvature lower bounds, and they imply the norm of Ricci and norm of Riemann. So this is kind of the best thing you want to actually get a lower bound for the scalar curvature. That's the best. But for upper bounds, you want to bound the full Riemann curvature tensor. Okay, so in that case, with Mike Friedman, Henry Shin, and Yunjia Zhang, we show that if we have a four-dimensional steady Ricci soliton that's also a singularity model, then the full Riemann curvature tensor is bounded. And so when you solve right away, you get the scalar curvature is bounded. And this is saying we could just upgrade to the Riemann curvature tensor. Okay, and so I won't go into the details of the proof except to just give the main idea. And the idea is, suppose that the curvature is unbounded. What would happen? Well, basically by Perlman's point picking, you'll be able to get a limit. And so you kind of have the sequence of points going off to infinity in the steady Ricci soliton. That's also a singularity model. And by dilating about these points going off to infinity, you get a limit, and you can prove that limit is Ricci flat. And this it's just from the point picking and the equation. The kind of idea is that the scalar curvature is bounded, but the Riemann curvature at those same points is going off to infinity. So the ratio is going off to infinity. Now, if we rescale so that Riemann is bounded, the scalar curvature will be zero. But if we have these things could all be made Ricci flows. So if the scalar curvature is zero, by the equation for the scalar curvature, the Ricci tensor must be zero. And then Perlman's no local collapsing theorem says that this Ricci flat manifold must have Euclidean volume growth. And then the theorem of Cheeger and Neighbor says that this must be asymptotically locally Euclidean. But asymptotically locally Euclidean puts constraints on the homology and cohomology of the underlying four manifold. And the idea is that this sequence of ALEs or approximate ALEs is happening in the steady soliton. The steady soliton itself is a singularity model of a Ricci flow on a closed manifold. So there must be an unbounded number of copies of these ALEs in this closed four manifold. And then the idea is that by cohomological arguments, you can show, together with some index theory, you can show that this is impossible. So ALEs look like S3 mod gammas. So gamma is the fundamental group of the S3 mod gamma. Its abelianization is H1. It's first shown that H1 is a direct double. It's a direct sum of the abelian group with itself. And then in that case, one can calculate using the Hertzberg signature theorem and Turing-Gauss-Bonnet formula, because infinity is controlled to get the contradiction. Okay, so that's just a very short recap. But the takeaway is that in 4D, for a steady soliton singularity model, the curvature is bounded. So what happens when we instead consider four-dimensional shrinking Ricci solitons and also assume their singularity model? Then the same argument assuming that the curvature grows above quadratic growth, you get the same ALE unbounded number of copies, you have the same ALE exclusion principle, then you conclude this by contradiction. So before the estimate was a scalar curvature as quadratic growth, and now we're just upgrading to Riemann. And there's a conjectured example due to Bamler, and if that exists, then this would be sharp. Okay, now you could also ask for curvature lower bound, not just the scalar curvature, but the question is what happens to the norm of the full, or actually what happens to, not the norm, but the Riemann curvature tensor itself. Can it be negative somewhere? And for example, like the FIK asymptotically conical shrinker does not have positive Ricci curvature, does not have non-negative Ricci curvature. So there's like negative curvatures. And then they establish the following bound. So kind of the idea is that there shouldn't be too much negative curvature off at infinity. And this is actually going to zero, right? Except it's going slowly to zero. And so the question would be, could it be improved? And perhaps one can get something like this. And but that's the best known. So it's kind of interesting. Some interesting open questions are: what are the best lower bounds for the Riemann curvature tensor for example, 4-dimensional Ricci Solitons? They don't assume that it's a singularity model, so you can always throw that in as a condition, and but it's not clear when you can use that. Okay, another remarkable theorem of Munteanu, it's Ovidio Munteanu and Jean-Pierre Wang, is that if you have the scalar curvature going to zero at infinity on a 4D shrinking Ricci Soliton, then you can upgrade that. Then that's going to force the full Riemann curvature tensor to go to zero, and not only that at a certain rate, which is just like that for asymptotically conical case. So this is a sharp result. So under this kind of basically a weak condition, you get a much stronger upgrade. Okay, and that actually condition is equivalent to the Ricci shrinker being asymptotically conical. And one question might be, let's maybe I think for right here, let's assume maybe it's not clear that it has to be assumed, but let's assume the scalar curvature is bounded, and ask this question whether just weakening the condition. And well, that's actually a bit related to this dichotomy conjecture of Munteanu Wang. That is it true that the scalar curvature goes to zero, or it's always bounded from below by a positive constant? It's not this case where, well, it's not going to zero, but the infimum is going to zero, like that. So it's going to zero in certain directions, but not others. And here's another wonderful result of theirs, which is that if you have the scalar curvature is bounded in dimension 4, so recall that if you're on a steady soliton, that would be automatic. But for shrinking, we only know quadratically growing upper bound for a scalar curvature. So if you make this assumption, then you can upgrade from scalar curvature to the full Riemann curvature tensor. Okay, and also, so the manifold, so one of the problems with shrinking Ricci solitons is, which is actually very well understood in the study case, is the number of topological ends, which basically nothing is known in the shrinking case. So I think it's not even known whether the shrinking Ricci soliton has to have a finite number of topological ends. Maybe there could be an infinite. But if you have an end where the scalar curvature is bounded uniformly from below on that end, then you have two possibilities. It's asymptotic, so it looks closer and closer, like there's a diffeomorphism that you can make the metric. starting to look as close as you like to this round cylinder. Okay, and so that's nice. That means that the end is very well controlled. It's looking more and more like the round cylinder. I mean, in this case, it's not even known if there's any other example besides the round cylinder itself. So if you're like asymptotic to a cylinder like that, could it be that it just has to be exactly equal? Or it could be weakly asymptotic to S2 across R2. Okay, and maybe I won't go into details about that. I'm kind of falling behind, but the idea is along certain directions and not along every directions, and we'll look at that. But that means under some glimpses at infinity, and here they're actually along integral curves to the gradient of the potential function, then you see this, or maybe the Z2 quotient. Okay, so that's says something about the first case is very satisfactory. The second case is the most difficult case, and that's where there's a lot unknown. Okay, so I mentioned the top-level edge is well understood in the steady case, and so there's this result of Muntiano-Wang again, and they show that in that case, for a steady case, it's very well understood. You're either the product of a line with a closed Ricci flat manifold. So you have that, or M has exactly one topological end. In other words, it's connected at infinity. And the remark was just what I had said earlier about the shrinking case. Okay, so the topology at infinity in terms of number of ends for a steady case is very well understood. Okay, so next I'll talk about the tangent flow at infinity. So I won't go into a technical definition of that, but the idea is you think of looking at infinity of a steady, so we'll look at steady Ricci Solitons. We'll look at the infinity, and we'll kind of look at where there's lots of volume, kind of go out where there's lots of volume. Technically, what you want to do is you want to take a conjugate heat equation coupled to the Ricci soliton as a dynamic Ricci flow, and then take what are called HN centers as the scale goes out to infinity. HN centers are basically where the conjugate heat kernel is concentrated at scale tau or time tau, backward time tau. And what do you mean by concentrated? Well, it means that the variance between the Dirac delta function and the conjugate heat kernel is optimal qualitatively. And then you kind of think of the conjugate heat kernel in some senses, even though it's spreading out, it's basically centered or concentrated up to scaling at these so-called HN centers. And that's where you start to take a limit. So it's taking like points that turn out to be in superimposing the dynamic case onto the static case. Is HN centers are going off to infinity, and those HN centers are where there's lots of volume and all that. And so that means kind of like when you have volume and kind of according to Perlman and afterwards, that you get good control geometry, including curvature, etc. Okay, so the idea is that this would be like the core reason that this is a singularity model, because there's some shrinking aspect of it. This is kind of a special case. Now, this can be a flat orbital. That's one possibility. And in that case, R4 mod gamma, gamma is a subgroup of 4, then the steady soliton must be a Ricci flat ALE itself. Okay, in that case. So that's in some sense, okay, we're happy in that case. And then in the other case, this other possibility is that we get a cylinder. So this is another shrinking soliton. So this tangent flow infinity is always going to be a shrinker. That's the theorem of Bandler. And it could be this shrinker. And then in this case, it has positive curvature outside a compact set. And there's examples due to Robert Bryant and Alexander Appleton. And there's even perhaps can be conjectured that those are the only possibilities. Well, there's the Z2 quotient. And then this is the most difficult case, the S2 cross R2. So we saw this pop up in the previous result about the asymptotics at infinity of Mutiano length. How much time do I have? Do I go through?
10 minutes. 10 minutes.
Okay, thank you. Okay, so that's about a core geometry. I'm going to talk about just various topics, maybe some of them a bit quickly. So there's this asymptotic volume ratio, and which is from kind of like Bishop-Gromov, but that requires Ricci non-negative to have that monotonicity and for this limit to exist. But for a shrinking soliton, you don't know that it has Ricci non-negative, so this may not exist, but actually it's proven to exist by Peng Liu, Bo Yang, and myself. And then what predated our result is that the asymptotic volume ratio is finite. So basically they showed that the ratio has upper bound. We just proved that the ratio exists. And so that means the volume growth is at most Euclidean. And then recently, it's I think published even this year, it's remarkable that there's actually a sharp estimate that the asymptotic volume ratio is at most 1. That means it's obtained by Euclidean space. And there's a gap there. It has to be small. If it's not Euclidean space, it has to be smaller than 1 by some constant depending on epsilon. And there's a characterization for when the asymptotic volume ratio is in terms of average curvatures over scalar curvatures over balls. And I'll skip that. Okay, so now we've kind of turned to volume. And in fact, it turns out that in his 2020 papers, Bandler proved that all singularity models, including those that are Ricci Solitons, must have Euclidean volume growth. So you have this nice upper bound. So then the question becomes, what is and that's sharp, of course, because of Euclidean space. Then what is a good lower bound? And Mutiano and Sessom proved this lower bound is linear, at least linear volume growth. And that you can kind of compare that to an old result of Yao, who proved that if Ricci is non-negative in general in Riemannian manifolds, you have at least linear volume growth. And then what happened is that it was actually sharpened to the following estimate, which is attained qualitatively on the Bryant soliton. And this is due to Bandler, Chan, Ma, and Zhang. And then this is in all dimensions. You have a steady gradient Ricci soliton. It's also a singularity model. Then you have this estimate. And this estimate is sharp on a paraboloid like the Bryant soliton. So we have these kind of good characterizations, sharp characterizations of what happens to the volume for steady solitons. And then this, I already alluded to these, so I don't think I will get into any more detail. I had mentioned this FIK shrinker, that's asymptotic, and the Bandler, Cifarelli, Conlin, Durrell shrinker. That's more asymptotic to S2 cross R2. But these are kind of used as to guide what one can hope for to prove estimates. And so, the hope is that Ricci solitons dimension reduce. So that means as you go off to infinity, they look like they're splitting like that. So that's not true. So that's kind of a big open question. Do they dimension reduce? So we decided to make this assumption that dimension reduces to 3 manifolds. That means that it could dimension reduce to different 3 manifolds for different sequence of points going off to infinity like that. But we're just assuming that you do get dimension reduction and then you get convergence. So we're assuming some very nice, a very strong hypothesis. Then the idea is that you would say that strongly dimension reduces is if that what you're converging to doesn't depend on the sequence. And then you have weak dimension reduces. So the picture maybe you could have is that on the Bryan-Soliton, it'll strongly dimension reduced to a 3-sphere, and then on actually something I talked about a couple of weeks ago in the colloquium, lies flying wing that would weakly dimension to reduce to S2 cross R, or the 3D Bryan-Soliton. So that's not unique. There's a couple of different ones, but so if we assume that we have dimension reduction to 3 manifolds, and the 3 manifold may not be unique, then either it's going to strongly dimension reduce to this S3 mod gamma, or weakly dimension reduce to the 3D Bryan-Soliton. So this is just kind of in agreement with the known examples. And then Lai proved the following existence for the flying wing. And this is S positive curvature operator is O3 symmetric, and it's Z2 symmetric. So it kind of looks like a flying wing in dimension 3. And in dimension 4 and above, it's a misnomer, because probably it'll be more like this, not like that. The asymptotic cone in dimension 4 and above is probably just a half line. And it's kind of flattening out. The asymptotic cone of the Bryan-Soliton is also a half line, but it doesn't flatten out. It's rotationally symmetric. And then there are very nice asymptotics for this case. I really won't go into detail about this, but they need to make some curvature decay assumption, which is somewhat weak, and it's expected because this is what you finally get in the end. So they're only assuming this, and then this is kind of the conclusion, where R will be like the distance to the origin. And so you again see the inverse linear lower bound. So this, and that's why you think maybe that might be the possible. Okay, so we know the scalar curvature can grow quadratically a priori. Can you get a better estimate? And it doesn't seem possible so far, but one thing is, like, if you're willing to say, well, almost everywhere, so you just you take an epsilon net, so the whole manifold, then you can find points that grow at most linearly. So you get a better estimate there. So where it's going quadratically is not a particularly big set. And the other thing is it cannot grow quadratically along a minimal geodesic ray. So the scalar curvature like that, that's another some aspect about how, like in what sense can it grow quadratically. But Bandler has proposed existence of a 4D shrinking soliton, which look like Bryan-Solitons here. So they'll weakly dimension reduce to the 3D Bryan-Soliton here, like that. And then I don't know why he thinks it grows quadratically. I think what it is that he made an ansatz that it's like, looks like a line, asymptotic to a line across a Bryant, and that the Bryants are scaling according to some function of this distance and all that. And then you just assume the potential function is a function of that. Well, the Bryant, some scaling of the Bryant potential function here, and then together with a function of R here. And so that sounded like a complicated calculation to see what it would look like. So I just put in like ChatGPT and said, okay, just make the ansatz that the curvature grows like R to some power, right? And then GPT says, well, that power is 2. So you kind of say, okay, maybe that's how he kind of decided it would be going. Right? But the idea is that these edges would not be geodesic. So the idea is, if it was like a wing, then it would be. But if it's more like curving in where the asymptotic cone is a ray, it wouldn't be. And so that wouldn't contradict the previous lemma that I proved like that. So Okay, so perhaps this is exists. It's very hard to say. And so then one can just ask, what is just the general picture that one is hoping for? And this is just speculative. But so far in 3D, all singularity models are shrinkers or steadies. You could hope that to be true in 4D. If not, you could hope that at least qualitatively it has a lot of similarities, or you can use shrinking and steadies to study general singularity models. And these are just, this list is just based on the known examples. So it's a very, I mean, you could just naively conjecture that anything possible is what is known, right? That anybody can do that. And this is what this is. So you can take that as just a list of what's currently known. Okay, so the philosophy is that the high curvature regions are close to pieces of singularity models. So the idea is like when the curvature is really, really large, you look under a microscope, you have to dilate space and time. It becomes more and more, the solution exists on longer and longer periods, almost ancient. So it's almost like a singularity model. And that if you can control these singularity models, their geometry infinity, that Ricci flow with surgery should be possible. Sometimes it's phrased as well, the first is really phrased as a canonical neighborhood theorem by Proman, and that's what he showed. And then the third case is that you can just speculate, since there aren't that many known examples, that maybe given the wild complexity of the smooth form manifolds, that the hope is that the Ricci flow singularity models is as simple as possible topologically and geometrically, given the hope that Ricci flow can approach, decomposing smooth form manifolds into geometric pieces in some sense. And then the last thing is just what I had said before. Okay, so I think I will stop here. Thank you very much.
Questions?
So this is part, I mean, I think you were saying this is part of a geometrization picture that you hope to.
Well, that I think Daimler's work is indicating, yes. I mean, most realistically, it might be, and even that is kind of like hopeful, right? But there would be an approach toward the 11/8 conjecture, simply because the 11/8 conjecture is.
What is that?
What it says is that it finally characterizes the following question, like which topological closed smooth form manifolds, so which topological, simply connected topological form manifolds emit smooth structures, are called smoothable.
Oh, yeah.
So it's reduced down because there's known for according to the intersection formula, is even or odd, to the even case and the spin case. So then it's reduced down to the following question, whether the signature of such a form manifold, a smoother form manifold, divided by the second Betti number must be less than or equal to 8/11. So, okay, so you don't have too much signature compared to the second Betti number. And that's the conjecture. So like the K3 surface.
That's true, then what happens? Sorry.
Then you know all the question, the answer to the question is what topological is simply connected form manifolds emit smooth structures.
Why do you expect the steady solitons to split at infinity? I mean, is there an intuition behind that, or it's just
wishful thinking? I think. Of course, 3D is very nice. That happens, but and all the examples are like that. We're assuming it's kind of like singularity models, and of course, singularity models can be rather wild, but they're kind of idealized limits where the magnification factor goes off to infinity. So you lose a lot of the fine understanding of singularity formation, right? That's why it had to be kind of part of for example, in the Hamilton-Perlman theory. That was just part of it, what singularity models are. But they seem like they might be, very idealized, and that's why one might hope for it. But not really a good reason, perhaps. Oh, I should say the following. I think Richard Bamler told me that, like for a steady soliton, if the scalar curvature is going to 0 points like that, then it'll split. For a shrinking 4D soliton, then if the scalar curvature sequence of points is subquadratic, it will split. So it's basically what happens at the top scalar curvature scale to see that splitting. I was hoping, I had this kind of no-blip conjecture where you hope, for example, what could be really strange is you could have a steady soliton, right? I mean, in 4D, so it has bounded curvature. And you could have a sequence of points going off to infinity where the limit itself is a 4D Bryant soliton. So you see this 4D Bryant soliton, then you see a bigger piece and more approximate. And this whole thing's an exact steady soliton. You see bigger and bigger parts of it. And it seems so anti-intuitive. But if it's not that, well, it still doesn't get you splitting, even if you can rule that out. But